Alright, so in this video we're going to be proving proposition 4.47. Now let H be a Hilbert space and let M be a self-adjoint subalgebra of L of H, which is itself weaker than assuming that it's a C-star algebra. Then the closure of M in the weak operator topology is a W-star algebra. Moreover, if M is abelian, then the closure is abelian. Right, so to prove this, we're going to use lemma 4.45, which we proved in video 4. So let's consider T and T prime to be in the closure, right? And these limits are in the weak operator topology. So we see from the first part of the lemma that the sum of elements in the closure are in the closure. Then because of the second part, we see that T alpha times T, well, we can pull that limit outside and find that that's also in the closure. Now using that fact and the third part of the lemma, we see that T composed with T prime is also in the closure. So by the fourth part of the lemma, we get that the adjoint of an operator in the closure is also in the closure. Moreover, if we look at a net in the closure that converges in norm, well, because uniform convergence is stronger than weak convergence, we find that it converges within the closure. So the closure with respect to the weak operator topology is closed with respect to the norm topology, and therefore it is a C-star algebra. And moreover, by definition, it's already closed in the weak operator topology, therefore it's a W-star algebra. Now if M is abelian, note that T alpha composed with T prime, because of the second part of the lemma, we can pull that limit out, and then because T alpha and T beta prime are in M, they commute, and then because of the third part of the lemma, we can put the limit back in. Now considering T composed with T prime, because of the third part of the lemma, we can pull that limit out, and then because of that previous fact, we have that these commute, and then using the second part of the lemma, we can put the limit back in. Therefore, the closure of M is abelian, and that concludes the proof. Now, an interesting corollary of this is corollary 4.48, where if you have a Hilbert space H and a normal operator T over H, we see that the W-star algebra generated by this operator is commutative. Moreover, we also see that if lambda T is the maximal ideal space of WT, then the Gelfand map actually provides a star isometric isomorphism from MT to the complex valued functions over the maximal ideal space. Now to prove this, first note that the W-star algebra generated by T is actually the closure of the C-star algebra generated by T in the weak operator topology. Now because of the spectral theorem, we see that this CT is commutative, so by our previous proposition, we get that WT is commutative. Moreover, because of the Gelfand-Naimark theorem, while WT is a commutative C-star algebra with lambda T being its maximal ideal space, therefore we have that the Gelfand map is a star isometric isomorphism. And that concludes the proof. In the next episode, we'll be taking a slight detour away from W-star algebras.